Greetings, student, greetings. Welcome to lecture 2 under polymer science. In this lecture, we are going to look at fundamentals of polymer technology, and then we are going to look at thermoplastic polymers, then thermosets, elastomers, and finally a guide to processing of polymers. So we recap on what a polymer is. We said a polymer is a macro molecule or a compound which consists of long chain molecules where each molecule is made up of repeating units. In other words, a polymer is a macromolecule made up of hundreds of monomers. So there may be thousands or even millions of these monomers in one polymer molecule. And the word polymer is from the Greek language. Poly means many, whilst meros means a part. Most polymers are based on carbon or are made of carbon. Some are made of other elements like nitrogen, oxygen, etc. Those that are made up of carbon are called organic polymers. In terms of the structure of polymers, they can be linear, as shown by the picture on the left. To my left here shows a linear polymer. Okay. And sometimes the polymer can be branched, which means it has some side chains. There's a main or backbone of the polymer. Then on each side you have these side chains. And we talked about the tacticity of these side branches, where we said some branches may be on one side, and in that arrangement they are known as isotactic, but sometimes they can be randomly arranged on the polymer. Okay. Then a polymer can also be cross-linked, as shown by this third diagram. And when a polymer is cross-linked, you have chains that are linked together through branching chains. Okay, so you have 1, 2, and 3 polymer backbones that are linked with these branches, the polymer. So it's cross-linking. Linear polymers, the monomers or the repeating units are joined together from one end to another in a single chain, and this chain is flexible, which means it's not so rigid, and the chains are kept together through physical attractions, and van der Waals forces play a role in keeping these chains together. And typically, linear polymers are made from monomers that have single end group, okay, or single end active sites. Remember when we talked about the free radical polymerization, for example, we have a chain that must have a lone pair of electron at its end, so that it can be able to bond to other monomers or initiator molecules. Some of the common examples of linear polymers: polyethylene, polyvinyl chloride or PVC, polystyrene, polyamides, and many more. And then when it comes to branched polymers, these ones have side chains or side branches. And these branches, they go out from the main chain or the polymer backbone. And the side chains are made of the same repeating units as the main polymer chain. So the monomers which make up the side chains are the same type as those that make up the polymer backbone. And these branches result from polymerization. And monomers that have two or more reactive sites or end groups are more likely to support this branching process. And for a polymer to classify as branched, its side chains or side branches, they should comprise of a minimum of one complete monomer unit. An example of a branched polymer is low density polyethylene LDPE, which is commonly used in making plastic bags, containers, textiles, electrical insulation, etc. And then when it comes to cross-linked polymers, we mean polymers where the polymer chains that are next to each other are connected in a three-dimensional network structure. And these connections are known as cross-links. And usually these cross-links are as a result of covalent bonding between the chains or between the side branches with the backbone chains. And these cross-links are normally permanent in nature. And once the cross-links between the chains develop, a polymer then becomes thermoset. We shall learn more about what it means to be thermoset. Examples of cross-linked polymers include epoxies, rubber, and various adhesives. We also have polymer structures or polymer arrangements, which is known as copolymer. And in a copolymer, you have a monomer made up of alternating monomers, different or two different monomers that are alternating in one polymer. For example, as shown here, this polymer is made up of monomers A and B, and they are alternating, okay, one following each other. Another arrangement can be the random one, where uh, the order is not following a systematic pattern. It's randomly arranged. We also have a block polymer arrangement where some monomers may follow each other to form a group, followed by another block or a group made up of another type of monomer, as shown on the diagram. So the monomers, they group together. Okay. Then in terms of the types of polymers, we can classify polymers either as plastics or rubbers, but also in terms of engineering, from an engineering perspective, You can also classify polymers as thermoplastic polymers, thermosetting polymers, or elastomers. Thermoplastics and thermosets are plastics. These two are plastics, whereas elastomers are rubbers. Okay. And thermoplastic polymers, at room temperature, they are solid, but when you heat these thermoplastic polymers, they become viscous. Okay. If you heat it to a few hundred degrees, they become viscous liquids. And this characteristic or property allows them to be easily and economically shaped into various shapes or products, because you can uh, mold them into a certain shape, then allow them to set or to become solid again. So you can heat and cool them repeatedly, and they won't lose their form and they will not degrade. And the thermoplastics are symbolized by TP. You can label them TP. So the key point here is that thermoplastics can be heat uh, and cool them repeatedly, and they won't degrade. Okay. Then thermosets, these ones now cannot tolerate repeated heating cycles as thermoplastic can, because they degrade. If you heat them, initially they soften and flow for molding, but if you increase temperatures, they may produce a chemical reaction which then harden them into an infusible solid, something like char, uh, like Tito, So they cannot be heat and cooled without degrading. These ones, they degrade, they turn into a char due to this chemical reaction which takes place on thermoset plastics. And these are symbolized by TS from the word thermoset. So uh, these ones, once they are heat, they then set into a permanent form. And if you further reheat them, they react chemically into and turn into char and they degrade. And then elastomers, which are mainly rubbers, these ones are a bit different from the first two in that they exhibit extreme elasticity or extensibility when you subject them to mechanical stress. Okay, so they are very flexible, they can stretch and so forth. Another issue is elastomers are also amorphous polymers, meaning that they don't form crystals, they are not crystalline. And at room temperature, the elastomers are generally or relatively soft. Some elastomers can be stretched by a factor of 10, and if you remove the stress or the tension, they go back to their original shape. So you can stretch a rubber 10 times its original length and it can go back to its original shape. And although they are The properties of elastomers are quite different from thermosets. They share some similar molecular structures that is different from the thermoplastics. And elastomers can also be thermoset or thermoplastic. So you have elastomers that can behave as thermosets and some that can behave as thermoplastic. So there are some rubbers which you can heat, they become viscous into a liquid. If you cool them, they solidify again like thermoplastics. But there are also rubbers which, if you heat them uh, in repeated cycles, they react and form char. The elastomers or the thermoplastic type 1 have significant advantage over the thermoset elastomers because the thermoplastic elastomers TPEs, they demonstrate processability that is similar to thermoplastic, and they are commonly used to make motor vehicle parts such as seals, gaskets, tire, tubes, and so forth. Sometimes they are also used as modifiers when mixed in hard plastics. Generally, in terms of market share, the thermoplastics are commercially the most important of the three types. So you find most products are made of thermoplastic, with about 70% of all synthetic polymers being thermoplastics. Then thermosets and elastomers, they share the remaining 30% market share. Uh, with the with elastomers being slightly above thermosets. So you have thermoplastic number 1, elastomers number 2, and lastly thermosets number 3. And then when compared to metals, the polymers exceed that of metals in terms of usage in global annual usage. More polymers are used than metals. Then examples of polymers are shown there. You see the thermoplastics. You have polyethylene, PVC, polypropylene, polystyrene, and also nylon. Whereas for thermosets, you have phenolics, epoxies, and some certain polyesters. And for elastomers or the rubbers, you have natural rubber, which is also known as vulcanized. But you also have synthetic rubbers, and synthetic rubbers have a usage rate that exceeds that of natural rubber. So natural rubber comes from plants, organisms, etc. And here are a few reasons why polymers are very, very important, why they are used more. The first reason is that plastics can be molded into various intricate shapes of parts, cars, uh, kitchenware, uh, packaging material, bottling, etc. And they are very compatible with net shape processing. On a volumetric basis, the polymers are cost competitive with metals. Okay, so you you pay less for polymers than you pay for the same quantity of metals. Uh, and then generally, the polymers, they require less energy to produce than the metals. And some plastics are even used as substitutes for glass because the plastics are transparent and can also be used as substitutes for glass in some applications. Here I have general properties of polymers. Polymers have low density when compared to metals and ceramics. They also have good strength to weight ratio for some certain polymers. So you find that for uh, a similar weight of polymer, it can exhibit huge strength of maybe it can resist tensile and compressive uh, uh, pressures. Then the plastics or the polymers are also resistant to corrosion. They don't form rust and they have low electrical and thermal conductivity. And then the polymers also have some disadvantages when compared to metals and ceramics. The first disadvantage or limitation is that they have low strength when compared to metals and ceramics. Then they also have a low modulus of elasticity, uh, and this means stiffness. And polymers, for example, plastics, can only be used in limited temperatures. Higher temperatures, they can melt or they can become liquid. Sometimes they can char if they are thermoset plastics. They exhibit viscosity, elasticity properties, and this can be a disadvantage in load-bearing uses where maybe you want to carry a certain heavy weight. Then some polymers, they degrade when they are subjected to UV radiation or sunlight and other forms of radiation. And then we talked about synthesis of polymers in the previous lecture, and we said the process uh, by which polymers are made is known as polymerization, and it involves joining many monomers together to form a macromolecule. And these small monomers are usually unsaturated organic molecules such as ethylene and unsaturated double or triple bond molecules. And an example is given here of the formation of polyethylene. And as you can see, it is formed using ethylene C2H4, which has a double bond here. So if you combine many ethylene molecules, you can form a polymer, which is polyethylene here, which is where the double bonds have been saturated now into single bonds. And there are various ways of polymerization. For example, we have addition polymerization. We also have step polymerization. But we also have coordination polymerization, among other methods. For uh, for addition polymerization, you refer to the previous lecture where we talked in detail about these processes. Then we also talked about the degree of polymerization, where we said the dp or degree of polymerization uh, is a ratio between molecular weight of the polymer versus molecular weight of the monomer. That's the degree of polymerization. And a higher dp increases mechanical strength and viscosity of the polymer. Okay, and this can affect processing if the polymer has strong mechanical strength and is too viscous. It makes processing difficult. And here are some typical values of uh, degree of polymerization and the molecular weight. For polyethylene, it has a BP of 10,000 and a molecular weight of 300,000. PVC has DP of 1.5 and molecular weight of 100,000. Nylon has DP of 120 and molecular weight of 15,000. Polycarbonate has DP 200 and molecular weight of 40,000. And then in terms of polymer structure, we have talked about this, where we have linear, branched, or sometimes cross-linked structure. In terms of cross-linked structure, you can have loosely cross-linked. Sometimes you can have tightly cross-linked. And for loosely cross-linked structures, it results in elastomers, the rubbers. Whereas for cross-linked, tightly cross-linked polymers, it results in thermosets. And the diagrams are here show the different polymer structures. The linear type is a single chain of monomers joined together, and it is usually flexible, this chain. A branched structure, it's a chain that has branches that are growing out of the main polymer backbone or main chain. Then the loosely linked cross polymer structure involves polymer chains that are next to each other and linked by some side branches in a 3D structure, but the branches are not so much profuse as compared to the tightly cross-linked one. You can see the tightly cross-linked one involves more uh, branches and more networks. And we said the tightly linked uh, structure results in thermoset, and thermoset, we said these are polymers which when heat in repeated cycles, they char. Okay, they are not able to be heat in repeated heating and cooling cycles because they char, they react chemically and they form char. But the loosely linked structures, they result uh, in elastomers, rubber or thermoplastics, which are able to be heat and cooled in repeated cycles without degrading. The thermoplastic polymers always are linear or branched or a mixture of these two. The branches, they increase entanglement among the chains, and it makes the polymer very strong in solid state. It also makes the polymer more viscous. So you see that polymers that are more branched are more viscous and are more stronger than the ones that are not so much branched or cross-linked. And thermosets, they possess a high degree of cross-linking, whereas the elastomers possess a low degree of cross-linking. The thermosets, they are hard and brittle. Yeah, if you bend a pencil, it breaks. That's brittleness. So thermosets have that typical nature. A common example of a thermoset is the adapter, electrical plugs or adapters. It's a typical thermoset plastic. Whilst elastomers, they are elastic, are extensible and are resilient. The cross-linking causes the polymer to become chemically set, and this chemical set is permanent. This reaction cannot be reversed. If you heat further, the polymer then degrades and bends to become a char rather than melt. In terms of crystallinity, it is possible to have amorphous and crystalline structures. However, the elastomers are generally amorphous or non-crystalline, whereas the thermoplastics or the thermosets, they can be crystal in nature. But the tendency to crystallize for polymers in general is much less than for metals and glass. For those polymers that can form crystals, the degree of crystallinity is usually less than 100%. And the crystallized region in a polymer is represented by long molecules that form crystals that are randomly mixed with amorphous material in structure labeled A. So you find that this region, the straight chains that are arranged in a fixed order, this represents the crystalline area, whereas the amorphous region is represented by these long chains or the folded lamella. Okay, and B, the crystalline region, is represented here with this lattice structure. As crystallinity is increased in a polymer, its density increases because the chains are tightly packed. You have more chains per volume area. So density increases, stiffness increases, strength and toughness also increases, and they become resistant to heat. And if the polymer is transparent in the amorphous state, it becomes opaque when partially crystallized. We have uh, comparison between uh, low density and high density polyethylene. So the difference between these two types of polyethylene is the other one has very low degree of crystallinity. It means that it may have arrangement similar to the diagram in A, whereas high density may have arrangement similar to B here. So high density polyethylene has more crystal regions than low density polyethylene. And as we can see, the low density polyethylene is at 55% degree of crystallinity, whereas high density polyethylene is 92%. Okay, so Uh, that's the major distinction between these two. That's why this one becomes low density, because as you increase crystallinity, the density increases. As you can see, specific gravity also slightly increases here for HDPE. And elasticity, the modulus of elasticity now for high density polyethylene, uh, okay, it's 700, whereas for low density it becomes 140 MPa. And the melting temperature increases for high density polyethylene, whereas that for low density it's lower. And the modulus of elasticity is more of inverse of elasticity. Okay, and linear polymers consist of low molecules with thousands of repeated monomers, and crystallization involves folding these chains back and forth uh, upon themselves, as was shown in this diagram. The chains are folded back and forth, and this causes crystallinity. The crystallized regions are called crystallites or crystallite. So this region is the what? The crystallite. And crystallites take the form of lamella, which is randomly mixed with amorphous material. Again, as was shown here, we have the lamella mixed with a region which is non-crystalline, which is the amorphous region. A crystallized polymer so is a two-phase system where you have crystallite region versus which is mixed or interspaced with an amorphous or non-crystalline matrix. Generally, slower cooling promotes crystal formation. And so if you cool your polymer slowly, not rapidly, you promote more crystal formation. So that's how HDPE is made. Versus low density uh, polyethylene. The cooling rates are varied. And mechanical deformation uh, in the stretching of a heated thermoplastic tends to align the structure and increase crystallization. And then sometimes plasticizers are added to reduce crystallinity. Okay? And this chart is showing the thermal behavior of polymers, the behavior of different polymers at two different temperatures. We have first temperature and the second temperature, Tg and Tm. And we have specific volume on the y-axis. We see that at temperature labeled Tg, okay, generally the polymers have similar behavior. However, the amorphous polymer has more density, okay, has a more density than the other two, and this density is increasing at a constant rate. Whereas for crystalline polymers, again, the density is lower than for amorphous, but also increasing at a constant rate. The crystalline polymer here is lower specific volume at this temperature. So it means the chains in a crystalline polymer are tightly pegged together, as we saw in the diagrams here. You see that in a crystalline molecule, the chains are tightly pegged together because they are folded on or folded on themselves, and this causes them to occupy what less volume. As we increase the temperature, uh, the volume starts to increase, but crystalline polymers are always have a lower specific volume than other polymers. And as we increase temperature, for amorphous, the rate even increases more, or the specific volume increases more, and they tend to become more liquid now. They melt or become liquid, usually viscous liquids, as you increase temperature. Then for crystalline or cross-linked polymers, if you increase temperature, the crystalline, they don't become liquid as shown here. Instead, they degrade. That's why the volume uh, increases up to a certain point. And then when making polymers, sometimes you add some chemicals which are known as additives to modify the structure of the polymer. So additives either alter the molecular structure or they add a second phase, in effect transforming the polymer into a composite material. Here are examples of types of additives that are added in polymerization. Some additives called fillers are used to strengthen the polymer or to reduce the cost. We have plasticizers which are used to soften or reduce the crystallinity of the polymer, and this improves flow of the polymer if you add plasticizers because you are reducing what crystallinity. Some additives are colorants that are added to produce some pigments or dye the polymer. Then we have the lubricants which are added to reduce friction and improve flow rate of the polymer. Some additives are flame retardants which are used to reduce flammability of the polymer. Uh, then some additives are what cross-linking agents which are used to improve cross-linking so that you develop thermoset and elastomer polymers. Some additives are ultraviolet absorbers. They help to reduce degradation from sunlight. And finally, some additives are antioxidants. They help to reduce uh, oxidation. Okay. The thermoplastic polymers, we talked about it, that they can be heated from solid to viscous liquid. Then you can return them back to solid if you cool them. And heating and cooling can be repeated as many times as one can without degradation of the polymer. And the reason why they behave this way is because they have linear or branched macromolecules that do not cross-link upon heating. The thermosets and elastomers now, when you heat them, they can react chemically and the reaction results in more cross-linking of the air molecules, which result in a permanent set of these polymers. Once they are permanently set, further heating can uh, cause degradation or charring. The thermoplastics have a low modulus of elasticity. Uh, Elasticity is much lower than for metals and ceramics. They have low tensile strength, and their tensile strength is about 10% that of metals, and they have much lower hardness than metals or ceramics, and they have greater ductility on average, so they can be shaped into tubes or cylinders. That's ductility. You can stretch them to thinness or thickness of one trace, and they can be stretched from 1% to 500%, 1% for polystyrene to as high as 500% more for polypropylene. And here is a diagram trying to show the relationship between temperature and deformation resistance of a polymer. As we can see, as we increase temperature, the resistance to deformation for crystalline polymers, it's a bit constant at first, but if you continue increasing temperature, the resistance falls sharply. And then for partially crystalline polymers, initially the resistance matches that of crystalline, but it sharply falls below that of crystalline. And then for uh, for amorphous polymers, the resistance also falls sharply and below the other two types. So the crystalline are more resistant to deformation than the amorphous types. And here are some physical properties of thermoplastics. They have lower densities than metals and ceramics, and with a specific gravity ranging from 1.2, and yeah, you can see that for ceramics is 2.5, whereas for metals it's roughly 7. So they are relatively heavier, less heavy, I mean, when compared to ceramics and metals. Metals are more heavy, and they have much higher coefficient of thermal expansion, being roughly 5 times the value of metals and 10 times that of ceramics. So if you heat uh, thermoplastics, they are able to expand more than metals and ceramics. They have much lower melting temperatures, and they have very good insulating electrical properties. They don't conduct heat and the electricity. They are poor conductors and so forth. And thermoplastic products include molded and extruded items, fibers and filaments, films and sheets, packaging materials, paints and varnishes, etc. And thermoset polymers or TS are more cross-linked in three-dimensional covalently bonded structures. and they are made, or they are uh, produced through a process called curing or setting. So thermosets are made using curing or setting process. They are cured, or they are thermoset. Common examples include pot handles, electrical switch cover, etc. And the structure of thermosets is always amorphous. There is no crystallinity and no glass transition temperature. And the thermosets are very rigid. The modulus of elasticity is 2 or 3 times greater than for thermoplastics, which means they are less elastic, very rigid. They are brittle, which means if you try to bend them, they break, and they exhibit virtually no ductility. You cannot stretch them or stretch them to increase their length. They are not so soluble in common solvents when compared to thermoplastics. They are capable of being of higher surface temperatures than thermoplastics, so they can tolerate higher temperatures when compared to thermoplastics. They cannot be remelted. If you try to heat them, they burn or degrade or char. And in thermoset polymers, we have 3 types. We have temperature activated systems when making these thermosets. We also have catalyst activated systems, and then we have mixing activated systems. That's the process of curing or setting. And curing can be done with temperature, catalysts, or through mixing. And it is accomplished at a fabrication plant that make the parts, and not the chemical plants that give the starting material. Curing caused by heat during the molding process, and the starting material of thermoset plastic is a linear polymer, which is uh, in granular form, so it's supplied as granules or pellets, plastic pellets or plastic granules, which are heat to soften the material. And once the material is softened, it is then molded into a certain shape. Uh, Further heating causes cross-linking, and this cross-linking results in setting of the plastic. And cross-linking, it occurs when small amounts of a catalyst are added. When it comes to catalyst activated systems, we incorporate some catalysts, and the catalyst is in liquid form. And in the absence of a catalyst, the polymer remains stable and liquid. Once you add the catalyst, the plastic is cured and changes to solid form due to the cross-linking. Then the third system is the mixing activated system, which is which means the mixing of two chemicals, which causes a reaction which causes cross-linking in a polymer. Sometimes you also add some heat to speed up the reaction. An example of polymers include the epoxies are produced using this system. Then when compared to polymers, thermosets versus thermoplastic polymers. Thermosets are not as widely used as thermoplastics, and this is mainly due to complex processing costs and complications that are needed for thermosets in curing. The largest market share of thermosets is usually with phenolic resins, and the usage is at 6% of the total market share of plastics. Yet, for thermoplastics, for example, polyethylene, market share stands at 35%. So you see that thermosets have relatively less usage, 6% compared to 35%. Examples of thermosets products include countertops, plywood, adhesives, paints, molded parts, printed circuit boards, and other fiber-reinforced plastics. Then the elastomers are another third group of polymers, and these are very elastic. If you subject them to low stress, they can stretch. Some can be extended to 500% or more their original length, and they can still return back to their shape. So we have two categories of elastomers. The first is natural rubber, and this rubber is derived from original uh, original or biological plants. We also have synthetic polymers. These ones are made industrially or chemically in the lab through polymerization process. So elastomers are long chain molecules that are cross-linked, just like thermosets. They owe their elastic properties to two features. Firstly, the molecules of elastomers are tightly kinked when unstretched. So they have a kink or a bend uh, as shown in the diagram here. You see these molecules have kinks or loops. They are shaped in kinks and loops. And this enables the molecule to be stretched as shown in diagram B. You can stretch and they can still go back. Another property of elastomers which results in elastic properties is that the degree of cross-linking is substantially less than for thermosets. So although elastomers are cross-linked, the cross-linking is less than for thermosets. And the diagram here we're showing a model of elastomers. They have kinks. They are also cross-linked, as you can see these black cross-links, but the cross-link are not as extensive as for thermosets. So you can stretch an elastomer if you remove the stress or the tensile stress, the molecule can go back to the original form. And when stretched, the molecules are forced to uncoil and they straighten. Initially, when you stretch, the natural resistance to uncoiling provides the initial elastic modulus of the aggregate material. So elasticity is the probability of going back to original shape. So there is the natural resistance to uncoiling. It gives initial elasticity. Then under further strain, the covalent bonds of the cross-linked molecules begin to play an increasing role in the modulus. So at first, you have natural resistance to elasticity. Then as you continue to stretch the molecule, the covalent bonds play a more important role in reducing elasticity and causing stiffness of the molecule. With greater cross-linking, the elastomer becomes stiffer and its modulus of elasticity is more linear. So the more the cross-links, the less the elasticity. So if you increase cross-linking here, you reduce elasticity of an elastomer or a rubber. And this chart is trying to show the behavior of different types of elastomers or rubbers when subjected to different levels of strain. As you can see, when you increase strain, uh, increase in stress here results in strain on hard rubber. It affects hard rubber more than for natural rubber, as you can see. If you put more stress here, hard rubber is affected more than natural rubber. And then in the middle is vulcanized or soft rubber. Okay, so hard rubber versus natural rubber, you have to make a choice depending on how much elasticity you need. Then we have a process known as vulcanization. Vulcanization is the equivalent thermosetting process of rubbers. Remember, we talked about curing of, of the plastics to thermosets. When it comes to rubber, the curing of elastomers is known as vulcanization. So we are promoting more cross links, thereby reducing elasticity of the rubber. It becomes a bit more set. So vulcanization is the term for curing in the context of natural rubber and some certain synthetic rubbers. Typical cross-linking in rubber is 1 to 10 links per 100 carbon atoms in the linear polymer chain, depending on the degree of stiffness desired. Then considerable, it's less than cross-linking in thermosets. So natural rubber, for example, polyisoprene, is a high molecular weight polymer of isoprene C5H8. It is obtained from latex, which is a milky substance produced by various plants. So latex, uh, if you detach a mango fruit from a tree, there is this sap, white sap which comes. It's also latex. Okay, and the most important plant is the rubber tree, and it grows in tropical climates. And latex is a water emulsion of polyisoprene. So it's water plus polyisoprene. And then some other ingredients are also added. So latex is simply polyisoprene. And polyisoprene is a polymer made of isoprene, C5H8. And rubber is extracted from latex using various methods that remove the water. And properties of natural rubber include high tensile strength, uh, high tear strength, and resilience or capability to recover shape, and they are resistant to wear and fatigue. The weaknesses of natural rubber are that it degrades when heat or when sunlight, oxygen, ozone, or oil is added, they also degrade. But some of these limitations can be minimized by adding some additives. And the market share of natural rubber is roughly 22%, that of the total rubber market. And some natural rubber products include some automotive tires, shoes, shoe soles, bushings, seals, shock absorbing components, and many more. In tires, uh, they add an additive called carbon black, which reinforces the rubber, serving to increase its tensile strength and resistance to tear and abrasion. Other additives include clay, okay? So we said other additives which are added to natural rubber products include clay, kaolin, silica, talc, and calcium carbonate, as well as other chemicals that accelerate and promote the process of vulcanization. And then we also have synthetic rubbers. And the motivation to make rubbers synthetically was mainly motivated during World War when natural rubber was difficult to obtain and they needed rubber for heavy machinery, military tanks, uh, shoe soles for soldiers, and other components. So the tonnage of synthetic rubber started to increase. Even now, synthetic rubbers are used more than natural rubbers. And the most important synthetic rubber is styrene butadiene rubber, SBR, styrene butadiene rubber, which is a copolymer. Remember what we said about a copolymer? It's a polymer which is made up of a alternating monomers. Okay, it's a polymer made up of alternating monomers, as shown here. So here, SBR or styrene butadiene is made up of two polymers, two monomers, butadiene C4H6 and also styrene C8H8. Okay, so it's made up of, and it's one of the most important synthetic rubbers. And the main raw material for most synthetic rubber is petroleum. So the petroleum industry, it's main industry that supplies raw materials for the rubber industry. Then we also have thermoplastic elastomers, and these behave like thermoplastic. A thermoplastic elastomer that can behave like an elastomer. So it's a thermoplastic that is maybe elastic And the elastomeric properties are, are not from chemical crosslinks but from physical connections between soft and hard phases in the material. So with thermoplastic elastomers TPE, the elastic properties of the polymer, they do not come from cross-linking, but more from physical connections between some soft and hard phases. And generally, they cannot match the properties of elastomers in high temperature and creep resistance. Examples of TPE include footwear, rubber bands, extruded tubing, wire coating, molded auto parts, but these are not used for tires. And then when it comes to processing of polymers, polymers are nearly always shaped in a heated, highly plastic state, and common operations in production of polymers include extrusion and molding. Molding of thermoset polymers is a bit more complicated because of the cross-linking, which makes the material more harder or more mechanically strong and more viscous in liquid state. The thermoplastics are relatively easier to mold due to, to their lower cross-linking. Then the rubber processing has a longer history than plastics, so rubber was used first than plastics, and rubber industries are traditionally separated from the plastic industry, even though processing is similar. Uh, so this has been a lecture on polymers number 2, where we talked about uh, thermosets, thermoplastics, and also elastomers. Thank you for listening.